Horses. We love them, we ride them, and they come in a whole host of sizes, shapes, and colors. Or do they? I'm going to mathematically prove that all horses are the exact same color. To do this, however, we're going to need to understand proof by induction. Firstly, proof by induction primarily works with discrete numbers, also known as whole numbers. Thankfully, there are no fractions of horses in our case. Let's look at an abstract example. Imagine a sequence like 1, 2, 3, 4, 5, etc., incrementing upwards all the way to a number we'll call n. Now imagine that we add all of these digits together, so 1 plus 2 plus 3 and so on up to n. If n was 4, then we would add 1 plus 2 plus 3 plus 4 and get 10. Easy enough, but adding all those numbers gets cumbersome if n is a higher number, like 1,000 or 10,000. Here's something we can do to get that value quicker. Take n plus 1, multiply that value by n, then divide the result by 2. The example of n equals 4, we can do 4 plus 1, multiply by 4, divide by 2, and there we have 10. But how do we know that this works for every value of n? We can have computers determine that it works for billions of values through simple repeated calculations, but the set of discrete numbers is infinite, meaning we can't know for certain without a proof. This is where mathematical induction comes in. The first step to proving through induction that our method always works would be to test the base case, or the lowest and simplest value for n. In this instance, that would be n equals 1. So we do 1 plus 1, multiply by 1, divide by 2, we get 1. Of course, we get the same thing if we sum the numbers manually, since the sequence is just 1. Step 2, the inductive step, contains the bulk of the proof, and begins with an assumption. In our example, we can assume that it's true that n equals k, implying that we can basically replace instances of n with k, like in our formula here. Using this assumption, we want to show that this is true when n equals k plus 1. We want to do this because if we can prove that it always works for whatever the next biggest number is, then we have proved that it works for all numbers. For instance, if n equals 1 like in our base case, and we can prove it works for n equals k plus 1, which is 2, then we know it works for every following number like dominoes. So, now, if we take our incrementing sequence starting at 1, it will go up to k rather than n, then increment once more to k plus 1, and we want to prove that our formula works in this case. So we set this sequence equal to the formula and replace the instances of n in it with k plus 1. If you look at this section of our sequence, it is equal to what we assumed to be true earlier, so we can substitute that in. Now I'll skip ahead a little bit for brevity, but if you do all the multiplication and addition, both sides are shown to be equal, proving our assumption correct and proving that our formula works for any discrete number. Now that we know the basics of mathematical induction, we can prove all sorts of things in the real world, including the fact that horses are all the same color. Okay, let's find our base case. This could be 0 horses or 1 horse, it doesn't matter because both will all be the same color. 0 horses necessarily can't be different colors from one another because there are no horses to compare, and the same goes if there is only one. For our assumption, let's say we have a set of horses called h, where n equals the amount of horses, and all those horses with the same color. Now, let h equal the sequence of horses leading up to horse n plus 1. So there's one more horse in this sequence. Let's take two subsets of h and call them h0 and h1. h0 is horse 1 through horse n, and h1 is horse 2 through horse n plus 1. It's the same set, offset by 1. The hypothesis says that because they both contain n horses, the horses in h0 are all the same color, and the horses in h1 are all the same color also. However, because there is overlap between the subsets, all the horses in both h0 and h1 must also be the same color as each other. This means that if n horses have the same color, n plus 1 horses are the same color. Translation, we have proven by induction that all horses are the same color, because this increments to every horse on Earth. However, I think most people have witnessed horses of two different colors, so perhaps mathematical induction doesn't quite work in the real world for some reason. The first reason one might think of would be that the set of all horses is finite, so there are not always n plus 1 horses. This is true, but a hypothetical infinite set of horses would also vary in color. This proof is actually completely sound, except for the case where n is 1. The proof necessarily relies on there being overlap between h0 and h1, so if there are only 2 horses, there is no overlap. This fault in reasoning can be used to quote-unquote prove many things similar to our claim, such as everyone having the same haircut or color of shirt. So, perhaps not all horses are the same color, but there are enough horses of each color, and don't our differences make us unique? Like and subscribe!